Okay, now here's some of the key buttons that we're going to need to push, but let me still walk you through it. Again, as I said, some students will say, yeah, that's nice, but I think I'll pass. But for some of you that are a little more tech savvy, maybe you'll say, hey, that's kind of nice. Can I use that on the test? The answer is yes, you can. Okay, it's not going to save the day, though. It's not going to do like every problem, but it can do sigma problems if we understand a couple things. First of all, you have to change the mode. Now I'm talking about like the regular big old mode menu, where down in the fourth line, we've changed to parametric mode, but we're going to skip on over here to SEQ, sequence mode. What this does is the calculator interprets formulas a little differently. It interprets them only with integers, which is always the way a sequence goes. It always goes from 1 to 2 to 3. It's always by integers. Now, in the, well, you got to go back to the home screen because that's where you type in commands. But in the list menu, now it might be a place you've never gone before. I actually had to find it again this morning. The list menu is second stat. It's a second option. It's near the top of the keypad. In the list menu, I have the ability to, in the ops submenu of this, to be able to display a sequence. So I go over to ops, down the sequence. Now, I'm actually going to do, I think it was number 92. Number 92 was a little simpler formula, but it was 15 numbers. And just to remind us, number 92 was 5 over 1 plus n. Even if you didn't get that last night, that's the formula, 5 over 1 plus n. And what we can do is we can type that formula in. But I want you to see that when you type the X button, that it actually turns into the letter n. And that's that whole sequence mode, because the letter n is always an integer. Now, the syntax is that you have to also follow the formula with a comma. If you've never pushed comma before, it's underneath the sign button. And then the letter n again, that's just part of the syntax. And then A to B. Now, A to B on the calculator represents the beginning of the sequence to the end of the sequence. In this case, it's the index, 1 to 15. Some of you with a different version of a calculator, you might actually be typing in these same 4 things around a sigma symbol. If you're typing them around a sigma symbol, you're still putting the same 4 things in: a formula, the letter n, and then the index 1 to 15. Now listen, it's not really that great because all this really does is display 15 numbers. And it doesn't even show the 15 numbers unless I scroll over. So it's kind of like, what did this really do? Well, again, it's displaying 15 numbers. What I really want to do is add these numbers, right? Now, if I want to add these numbers, then I need another command, and it's the summation command. So what we're going to do is we're going to actually combine 2 commands together. Now, to do this, I have to go back to the list menu, but this time slide over to math, and then down to sum. Now, the sum actually is the sigma symbol. But what I'm going to do is a sum of a sequence. And that's why if you're looking up at my screen, you should see that we actually are combining 2 commands. Again, I'm going to do the sum of the sequence. What sequence? Well, the same one that I just typed in the previous step. So I kind of have to like retype it. Okay, so to get the calculator to do a sigma, we have to do a sum of a sequence. And then, of course, using the same syntax. I don't want you to get frustrated with this. I'm happy to check out what's going on if you are not able to get 11.9. I really do want you to realize, though, that the calculator is adding 15 numbers, which is kind of nice. I mean, think about it. It could actually add 100 numbers. But you have to try to get this code to work.
I did get 11.9, but instead of typing it all in, once you do that, can you just puts down second answer.
Nice job. You definitely can do that. If you had already typed it, you can hit second answer, and it'll sort of like insert that code in there for you. Good.
Do I have to plug my numbers into this, or what do I do? I don't know.
Yes, you're gonna put the formula right there.
Okay.
That stands for expression. So that's going to be your 5 over 1 plus n. And then the next thing is going to be it's going to be the same 4 things. You're just going to put them into that little menu.
Okay. Where's the M?
That's your X button. Feel free to tinker around with this. I'm not going to go through it like for every problem, but you could do number 94, the one that Anna asked about, or not. Like I said, you don't need to be able to use this, but I do let you use it if you want to, when it comes to, again, to like a graded activity. Did you need anything else off that screen? Okay. Is there anything else you want to talk about with the homework? As I said yesterday, there's a nice review that we'll do tomorrow. It is pretty nice. It kind of puts all the chapter together, and you'll see a few more sigma problems. What I would like to do today is go back and not so much revisit something, but finish something. We're going to finish something that is technically part of the topic 6.3. Okay, now if you care to know, that'll involve repeated decimals, and it'll also involve this idea known as a limit. So this is a little strange because it's kind of like we're jumping back to a topic, but the reason that this fits into 6.3 is you're going to find out that both of these little lessons involve infinity. They both involve infinity, which was really what section 6.3 was doing. Okay, just kind of make sure you're keeping track in your notes in a way that makes sense to you. And let's talk about repeated decimals. You know, why all of a sudden repeated decimals? Well, as you'll find out, repeated decimals actually technically are a infinite series. A repeated decimal is really an infinite series. Now, when I say infinite series, if you kind of get like a little nervous, you're kind of like, oh, what's he talking about, an infinite series? Don't worry, we actually did some of them yesterday. Okay, but basically an infinite series is when we're adding together an infinite amount of numbers. It turns out that a repeated decimal is exactly that idea, adding together an infinite amount of numbers. But as you're going to see, technically, it's an infinite amount of fractions. Okay, we love fractions. Imagine having an infinite amount of fractions. Let's say you had the repeated decimal 370, 370, and on it goes. Okay, now if you want to write that as a fraction, and by the way, not just like put it in your calculator, which I don't know if your calculator is really going to work, you know, like kind of hit your fraction button on your calculator. That's kind of cheap. Think about this with me. Although we sometimes just say 0.370, isn't that really 370 thousandths? You know, there's a time where we would have spoke it that way. We would have said it that way. Let's go back to that time, because it's true that the next one is really 370 millionths. Now, sometimes that takes a little bit of thinking, because like, oh, how many decimals did I move? But I moved 3 more decimals, so I add 3 more zeros. So 370 thousandths, but then I have 370 millionths. Well, the next one's going to be 370 billionths. And that's why we usually don't talk that way, because we kind of get lost as to what spot we're at. But really, this decimal, this repeated decimal, isn't just these fractions, but it's the sum of these fractions. because it's like I'm adding another 370, and then I'm adding another 370. Now, there's something special about this series. Remember, series just means we're adding numbers. Okay? I know we're adding all these fractions now, but there's something special about this series. And that is that it is geometric. Now, the reason it's geometric, okay, the reason that it's geometric is because it has an R value. And really, it's the R value that should be the first thing that you kind of discover. What do we mean an R value? Remember, that's just something that you're multiplying by to get to the next, to the next, and to the next. Well, every one of these fractions is being multiplied by 1,000th. To say it another way, every one of these fractions is just 3 more decimal places. And if I multiply by 1 over 1,000 or 1,000th, it's going to have that same effect. Now, a couple days ago, it actually was a couple weeks ago, but a couple school days ago, when we said that we had something that was geometric and the R value was less than 1, then this thing can be found, that is, the sum of this can be found using the infinite geometric series. And the infinite geometric series is basically another way to describe the sum of all of these fractions. Remember how it goes? You just need the first number, 370 over 1,000, divided by 1 minus that common ratio. Now here's what I want you to think about before you worry about calculating this answer. Just pause with me for a second, because this is more important than trying to figure out this answer. I want you to understand that this statement, this formula, this number, I mean, it's a number here, is the same thing as adding all of these fractions, which is the same thing as this repeated decimal. So a repeated decimal is the same as an infinite series. In other words, adding all of those geometric numbers. Okay, now we do need to calculate this, but let's kind of approach this a little bit without a calculator. I want you to become this kind of student. First off, the denominator, 1 minus 1,000, that should be something that we can think about a little bit kind of mentally, because 1 minus 1,000th is really just going to be like 1,000 over 1,000 minus 1 over 1,000. You're going to end up with 999 thousandths. You're just taking 1 away. Okay, so again, I made a common denominator in my head, and we end up with 1,000 minus 1, 999 thousandths. Now, if you're dividing by 999,000, that's the same as multiplying by the reciprocal. If I multiply by the reciprocal of 999 thousandths, well, that's convenient, because that ends up giving me these thousands in nice, 2 nice spots. That is 2 spots that are able to cancel. $370, I think I've seen that number before, all over 999. Now, if you do some simplifying, I think we can simplify this. You could simplify it by 37. That would take a little bit of fooling around on your calculator, kind of finding that common value. But if I divide everything by 37, I can get 10 over 27. Just reducing it. And of course, 10 over 27, if you care to check it as a decimal, will spit back out 370, 370, which is, it's good to check it. There definitely is I guess I'll call it a pattern to this process. In other words, you do a few more of these, you start to notice the same thing happening. I'm going to do one more, And then when you take a look at your homework, okay, there should become a point where you're kind of like, okay, I see how this sort of always works. So let's dabble with one more. Maybe give you guys a chance to mess around with part of this. I threw a little curveball at you here. The whole thing is not repeating, because I want you to see that any number, especially a decimal, but any number can be written as a sum. You know, here I could say that 1.83 is the same as 1 plus 8/10. That'll give me my first decimal. And then plus 3/100, and then plus 3/1000. Now this one's you'll find is the repeated part's a little easier because we're only moving the decimal one place each time. So 3/1000 plus 3/10,000, and I'm sure you can guess what the next and the next would be. You want to understand that it's the repeated part that is the series. The number 1 doesn't repeat, 8/10 doesn't repeat, so I don't want to add those up like a series. But these numbers here represent, once again, a geometric, in fact, an infinite geometric series where the R value, now think about this. This is like the thinking part of the problem. We have to understand that each one of these fractions is actually only adding one more zero. So I would only have to multiply by another 10, another 1/10 technically, but our R value is only 1/10. Do you want to see if you can write the series? It's an infinite series. You're only writing it for the repeated part. So once again, please ignore the 1 plus 8/10. I like that you're trying to do it. It's only the second time you've seen this, but be careful. I don't want you getting bad habits. Like, you definitely need the first term. You need 3/100, not just 3, but 3/100. You need the actual term. One minus 1/10, 1 minus R, now 1 minus 1/10 is like 10/10 minus 1/10, 9/10. You're always going to find some kind of canceling. Multiply by the reciprocal of 9/10 is multiplying by 10/9. Again, you're always going to find some canceling. I encourage you to find that canceling as much as you can without a calculator. I can divide one of these zeros off. I can check out or check off some of this 3, divide off some of the 3. One over 30. We only end up with numbers in the denominator. Now, maybe you kind of say, okay, so what are we trying to do here? We're trying to write 1.833 as a fraction. Okay, it would be a little silly to say that 1 over 30 is the same as 1.833. But the 1 plus 8/10 plus my 1 over 30. Now that, if you put all 3 of them together, is going to give me my full decimal. So we have one more, I suppose, calculation. We have to try to write this as a fraction. Basically, we need to get one common denominator. Okay, and again, I encourage you to think this way without a calculator as much as possible. Your common denominator is 30. You can multiply the second fraction by 3 so that you can get 24 over 30. Everything's all set now. 30 plus 24 plus 1. 30 plus 24 plus 1 is 55 over 30. You could reduce that. When it comes time to do this on like a test, I'm not going to be too picky, but there are 5s that are common to this. So we could reduce it by 5s and get 11/6. Okay, and that's going to give you your original decimal. Repeated decimals, kind of an odd concept suddenly popping up with infinity. But basically, it's an infinite geometric series. Now, one more kind of mini lesson here. We're actually going to talk about something that is truly a pre-calculus concept. Okay, if you're like, did I miss this, yesterday? No, we didn't talk about limits. Actually, you'll talk about limits a lot in calculus next year, but I want to sort of scratch the surface and help you see how limits that involve infinity also connect to sequences. You have to understand, though, that we're not going to be adding numbers together. Like, it's kind of like a whole different thing. We're not going to add numbers. We're not going to come up with a sum. Okay, what we're really going to do is we're just going to analyze a pattern, almost like going back to the first couple days where we were just looking at patterns. Now, a limit, first off, what is a limit? Okay, it's actually, by definition, an intended y value. A limit is an intended y value. And really, the purpose of the next 15 minutes is to try to help you guys figure out what we mean by the intended y value. And there's actually different ways to find the intentions of a function. There's different ways. So understand that I'm actually going to be showing you, I believe, 3 different ways, okay? And all of them lead us to the same answer. Eventually, you'll kind of pick you'll pick which method you want to use. But just to help you kind of get set here, we're going to look at this through many different lenses. All right. There's even a little bit of notation that you have to see, but it's not too hard. And that notation is this abbreviation for a limit. So we abbreviate the word. You see an X with a little arrow here. That stands for x approaching infinity. And you would read this as the limit as x approaches infinity of x plus 1 over x squared. Okay, now just kind of go with this a little bit. Don't feel like you have to have it all figured out. In fact, I'm going to show you a numerical way to think about this limit. And that is by thinking about lots of inputs and outputs. Okay, now you don't need to worry about doing this on your calculator yet. Maybe just kind of watch, just so you understand. I have typed in the function x plus 1 divided by x squared. I actually typed it in as an equation. If I input x values into that equation, maybe I input the number 1, maybe I input the number 2, maybe I input the number 10. If I input numbers into that function, I get certain outputs. Now what I did right here is I did this on a table, but again, it might be better if you just kind of watch the first time. Okay, and in the table, it shows what happens if I plug in 1. It's actually not hard to see. If you plug in 1, you just get 2 over 1. Well, that comes out to be 2. If I input other numbers, now as you can see that I'm starting to input larger numbers, I get other outputs. Okay, now these outputs seem to be some strange decimals. But the reality is that these strange decimals are getting smaller and smaller. And they are intending to eventually reach a certain y value. They're intending to reach a certain y value. And maybe an educated observation, a student would say, well, they look like they're intending to reach 0. Okay? Again, an educated observation may note that they keep getting smaller. What about a graphical approach? Look at the graph of this equation. Now, you've graphed things before, so this is kind of like just good old algebra, graph an equation. If I graph the equation, I have to kind of see what it means to go to infinity. Now, to see what it means to go to infinity would see moving to the right. So when I move to the right, I see this graph's y values going down closer and closer to the x-axis. And these y values that are getting closer and closer to the x-axis are also getting closer to 0. Okay? And finally, if you look at the algebra behind this equation, you can note something interesting about the numerator and denominator. Now, the numerator has as its largest exponent x to the first power. The denominator has as its largest exponent x squared. That's called the degree. Now, the degree of a function kind of overrules what happens when you go to infinity. What that means is that the highest exponent is going to kind of take charge when I start looking at big numbers. So I can kind of simplify this equation to just be x to the first over x squared, which is really just the same as 1 over x. Now, we've talked about this before, but if you think about it, as x gets really big, what that would mean is I'm taking the number 1 and dividing it many times. Well, what happens if you take 1 and you divide it over and over and over? That's right, it's going to get closer and closer to 0. And that would be more of an algebra approach. Okay, now the intended y value of this function as x gets really big is ultimately the number 0. We showed it with a table, with a graph, or maybe just by looking at the algebra. Let's try another one. Again, this is a new idea, and I don't want you to make too many conclusions without seeing a couple more situations. Four x cubed plus 6x all over 2x cubed. 4x cubed plus 6x all over 2x cubed. And by the way, we're doing the limit as x approaches infinity, which really means to try to figure out the value of this as x gets really big. Now, I said that maybe you just want to watch, but I know that you also want to know how to do this. And so if you're going to use a calculator method, I don't want to be hiding anything from you. I'm just typing in the equation. So if you're going to use a calculator method, just like you've done other times in the y equals screen. By the way, you had to change your calculator back to function mode, didn't you? You have to change it back to function mode. We were in that sequence mode, but you got to mess around with that. If you are using a calculator method, mind your manners and use parentheses around a numerator and a denominator. That's actually a really big deal. Often that's like the number one mistake kids make is just typing it in. So you got to use parentheses. Now, I'll tell you, that table thing that I did, a lot of people don't use it, okay? But it's still a viable option. The reason a lot of people don't use it is because it's cumbersome. You have to set up the table. And just being honest with you have to set up the table. If you've never done this, it's second window. And if you're also like, yeah, I don't know if I really want to do this, you probably don't need to. But second window is the table setup. And you kind of have to like start back at the beginning. You have to start back at 1. Now I'm choosing to change by tens. That means that I'm plugging in increments of 10 because I kind of want to get to infinity a little faster. Now, could you plug in increments of 100? Yeah. So you got to look at this setup screen and understand that it then determines what I'm going to see when I go to my table, which is second graph. Whoops, second graph. Now, when I go to the table, I see what happens when I plug in 1, which I always like to plug in 1 because that's easy to do. If you plug in 1, you just get 10 over 2. 10 over 2 comes out to be 5. If I start plugging in bigger numbers, like I kind of jokingly said, I get to infinity a little faster. Can't really get to infinity, but I'm trying to plug in bigger x values. Now, an educated observation, a student should look at this and say, it looks like these y values seem to be getting closer to the number. Let's look at the graph. Now, if you look at the graph, you want to be able to see what happens when you go to infinity. That means going out to the right. It looks like this graph is dipping down, but it seems to be leveling out. And it seems to be leveling out at something we call horizontal asymptote, which we actually will discuss in some more detail in a few months. But you've seen horizontal asymptotes, and I just want you to visually observe that this graph appears to be stopping at that y value, which, as you could see from the other screen, appears to be the number 2. What about this algebra method, which, just to kind of fill you in, that's what most kids end up using because it's easy. Look at this algebra method. If you take the degree, now the degree is the largest exponent and everything that comes with it. So it's 4x cubed. The degree, well, there's no choice. It's 2x cubed. Listen, I know this is a new idea, but if you think about what I'm saying mathematically, the highest exponent is going to overrule what this function does because the highest exponent is going to have the most effect on a graph when you think about infinity. So that's why I'm allowed to just kind of grab the x cubes. And then what can I do with this? Oh, I can do math. I can do algebra. Cancel the x cubes, simplify the numbers, and boy, geez, look, you end up getting 2. And that's the limit. That's the intended value of this function. We saw it with a table. We saw it with a graph, which actually was an asymptote. And then it looks like just by the algebra, it works. Why are we talking about this today? Technically, there's a pattern behind this. And the pattern is that it keeps approaching these values. Okay, again, it's really a pattern, which is why it's in this chapter. One more. How about the limit? I should say the limit as x approaches infinity. That's how you say that. The limit as x approaches infinity, x over x squared. I'm just going to pause because it's always good to let you guys do a little bit of thinking. Maybe you're going to do calculator thinking. Maybe you're going to use that degree idea. I'll share with you that the answer to this is, well, it's a little different than the previous 2 problems, but you can still think about it. There's nothing wrong with graphing it. I mean, I showed you that. But it's a different behavior. Like, you should be concluding that it looks like the value of this graph, the y value, just keeps going up and up. You're not missing anything. It just keeps going up. Okay. How about if you do the degree thing? Yes, you can just take the highest exponents. and basically simplify and work with x to the fourth over x squared. Well, that's just x squared. Now, if you think about big numbers, because that's what infinity is, it's big numbers. If I keep squaring numbers and I square bigger numbers and square bigger yet, okay, those numbers themselves are just going to continue to get big. So the intended y value, there isn't one. There is no intended value because the limit keeps getting bigger. The answer itself is actually infinity. Now, you'll learn in calculus next year that to say that the answer is infinity is to actually say that there's no limit because there's no intended value. All right, so a small discussion on limits, which you'll continue next year. We'll actually continue a little bit tomorrow when we do the review. Practice these two ideas a little bit. There's a homework helper that's still hanging out. It's homework helper 6.3, and at the bottom of it was F through K. So F through K will match with these two little topics today. Okay, that homework helper is still on Google Classroom. I believe it's still the last post, if not right around the last post. You should see it there.